Hello everyone, I am Sanjeev and I welcome all of you to searchingai.com and CCO 1011, and this is the first presentation in convex and combinatorial optimization. So this presentation is just an introduction to the mathematical optimization. So in this presentation, I will first of all introduce you to the mathematical optimization or just the optimization. Then I will discuss the applications of optimization and then solving the optimization problems and different algorithms such as least squares and linear programs. And then I will discuss the convex optimization and then the nonlinear optimization and local optimization, global optimization, and the role of convex optimization in nonlinear programs. So let's begin with the general mathematical optimization. So a general mathematical optimization problem is minimizing a function subject to some constraints, where we have to minimize the objective function f naught of x subject to constraints that each fi should be less than or equal to bi. That is, we need to minimize the objective function f naught of x, and we have m constraints that each x that is feasible should satisfy the constraint that fi of x is less than or equal to bi, and we have m such constraints. So the overall problem is to minimize the objective function, minimize f naught of x, subject to constraints that fi x is less than or equal to bi for I equal to 1 to m. So here are the terms which are defined as f naught of x is the objective function, is a function which maps a vector in Rn to a real number. Each fi is a constraint, inequality constraint, and it maps a vector in Rn to a real number R. And each bi is a constant and bi belongs to R. So we have m constraints that each fi of x should be less than or equal to bi, and subject to these constraints we need to minimize the objective function f naught of x. So here x is an optimization variable and is a vector in Rn with n components x1 to xn. So the optimal solution to this optimization problem, minimize f naught of x subject to constraints fi of x is less than or equal to bi. The optimal solution is denoted as x. The optimal solution is denoted as x star, and x star is the optimal solution to the optimization problem such that the objective function is minimized. So if there is any variable z in the domain of the function, where the domain of the function is defined as set of all vectors z in Rn such that fi of z is less than or equal to bi. So any vector in Rn which satisfies the constraint that fi of x is less than or equal to bi belongs to the domain of the function. So optimal solution x star is a value of the optimization variable x which minimizes the objective function f naught of x among all feasible points, and optimal solution is the value of the optimization variable among the feasible points for which the objective function is minimized. That is, the f naught of x will give the minimum value for the optimum value of the optimization variable x. So let's discuss the two classes of the optimization problems. So a mathematical optimization problem will be a linear program or a non-linear program. So for a linear program, if the objective and constraints are all linear, then the mathematical optimization problem is known as a linear programming problem. And if any of the objectives or the constraints is non-linear, then the optimization problem is a non-linear program. So for a mathematical optimization problem to be a linear programming problem, all the functions, that is f naught of x and all fi, should satisfy this constraint. That is, this f naught and fi, each fi should satisfy the constraint that alpha times that fi of alpha x plus beta y is equal to alpha times fi of x plus beta times fi of y for all x and y in Rn and alpha and beta in R. So if all the functions f naught and fi's satisfy this constraint, then the programming problem is known as the linear programming problem, and if any of the fi violates this constraint, then the problem is non-linear programming problem. So here comes the convex problem. So a convex programming problem involves all the convex objective and constraint functions. That is, all the objective and constraint functions are convex and they satisfy the following condition, That is, each fi, where fi involves f naught and all the fi's in the constraints. So each fi should satisfy the following condition: fi of alpha x plus beta y is thus equal to alpha times fi of x plus beta times fi of y, where alpha and beta belongs to R. Alpha comma beta satisfy the condition that alpha plus beta is equal to 1, and alpha and beta are both greater than or equal to 0. And the variables x and y belongs to Rn. So if any of the function, that is, if any of the f naught or fi's in the constraints violates this condition, then the optimization problem is a non-convex problem. And we will see the geometric interpretation of this condition, that is, fi of alpha x plus beta y is as equal to alpha times fi of x plus beta times fi of y. So for a linear programming problem, the equality holds, whereas for a convex optimization problem, inequality holds. So let's begin with the applications of mathematical optimization. So the overall problem is choose the best possible optimization variable from a pool of vectors in Rn satisfying the constraints. So this problem can be formed in different forms and can be applied in different areas. So here are some examples like regression, SVM, and regularization. So all these problems are optimization problems. In fact, these are convex optimization problems, but that's not the point of discussion. And the constraints can be the requirements that cannot be overruled. So we can put constraints on variables, such as the variable should be greater than or equal to 0, or any prior information can be modeled as a constraint. So in finding a particular model where variables are parameters in the model, so constraints can be the prior information, like in the Bayesian problem. If you have the knowledge of prior distribution about the variable or the parameter of the model, then it can be added as a constraint to the optimization problem. And in one of the presentations, we will see that solving a Bayesian problem is equivalent to solving a regularized problem. So another example is in path planning. So in path planning problem, your objective function could be the time step. So you want to reduce the number of time steps required to reach the goal location from your source location, and the constraints can be such as the robot or the vehicle should avoid the obstacles in the path. So the path planning problem, and in fact many of the research papers in the path planning involve some kind of optimization problem. So one of the applications is in decision making systems, such as multi-criterion, bi-criterion problem. Suppose we have two functions in the objective function f naught of x, that is, the objective function f naught of x is the sum of two functions f1 and f2, and f1 and f2 are such that increasing f2 decreases f1. So to find the optimal solution, we generally do a trade-off analysis using the Pareto optimal curve, and we will discuss it later. So this is one of the applications of the mathematical optimization. In the finance, we do portfolio optimization, where we seek the best way to invest some capital in a set of n assets. So the optimization variable, which is the vector in Rn, has the components x1 to xn. Each xi could be taken as the investment in ith asset, where x belongs to Rn is the overall portfolio allocation across n assets, and the constraints can be the budget, such as the investment cannot exceed your total budget. So the portfolio optimization problem can again be framed as a mathematical optimization problem, in fact a convex optimization problem, which we will see later. And here again the path planning algorithm ECN will involve the decomposition of obstacles into convex sets, and here's a link. You can visit the page for the ECN algorithm. So this was all about the applications of the mathematical optimization. In fact, the applications are not limited to the applications discussed in this presentation. I have just mentioned some of the applications. In fact, this course will specifically focus on the path planning, so most of the applications will be in the path planning. But mathematical optimization is not restricted to these applications. In fact, almost every problem in machine learning is finally an optimization problem. So in general, it is quite hard to solve a general mathematical optimization problem, and even if we can solve the problem, it depends on several factors such as the number of variables in the problem, the number of constraints in the problem, and is there any special pattern such as sparsity or the diagonal matrices, which again implies a sparsity pattern. So the solution depends on these factors. The time taken by the solution and the efficiency of the solver and the reliability of the solver depends on these conditions. So here are some classes of the optimization problems. So first is the least squares, which is again the convex optimization problem, since the objective function is a convex function. Linear programming problems, which by default are convex optimization problems. The third one is convex programming or the convex optimization, and the last one is nonlinear programming problem or the nonlinear optimization. These problems are not linear and also not known to be convex. So these generally involve two kinds of solution. One is a local solution and one is a global solution. So here comes the least square problem. So these are readily solved and have the analytical solution. So a simple unconstrained and unregularized version of the least square is minimize the objective function f0 of x, where f0 of x is norm of ax minus b, where the norm is the L2 norm, is square of the L2 norm. Here x is the optimization variable and is a vector in Rn. A is a data matrix and A belongs to R k cross n, and B is a vector in Rk. So the problem is to minimize the L2 norm, the square of the L2 norm of Ax minus b. So the solution is pretty straightforward since the problem is convex and have a unique solution. So the solution is found by differentiating the objective function and equating the result to 0. So by doing so, we obtain an analytical solution for the optimization variable x, which is given by A transpose A inverse A transpose B. So we will discuss the derivation of least square problems, and we will analyze least square in much detail in the later presentations. So this is the analytical solution and is given as A transpose A inverse A transpose B. So in general, there are no analytical solution to the optimization problems, but least square is a special case and has an analytical solution. So there are three important points to discuss about the least square. The first is that these problems are readily solved with hundreds of variables and thousands of terms if we do not exploit any sparsity pattern or any spatial structure in the data matrix A. The second is that if we can exploit any spatial pattern such as sparsity pattern in the data matrix A, then a very large problem can be solved very reliably and very efficiently. The third is that the problems which demand the real-time computation with millions of variables are still challenging, and this boundary is increasing. So there are also several variants of the least square problems, such as the regularized least square problems, which we will discuss later, and the L1LS package by Professor Stephen Boyd is an example of the powerful solvers for the regularized problems. So the regularized problems were generally solved by using the lasso algorithm, and the new package, which is known as the L1LS package by Stephen Boyd, solves the regularized least square problems very efficiently. So here comes the linear programming problem, and as we have discussed, in a linear programming problem, all the objectives and constraint functions are linear. So mathematically, this can be expressed as minimize C transpose x subject to constraints AI transpose x is less than or equal to BI. That is, we have to minimize this function subject to constraint that each AI transpose x should satisfy the constraint, that is, it should be less than or equal to BI. So here variable x is a vector in Rn, and C, A1 and Am are all vector in Rn, and all BIs are constant. So here the objective function is a linear function in x, and the constraints are also linear in x. So a linear programming problem is minimizing a linear function subject to linear constraints. So in general, there is no analytical solution to linear programming problems. There is the least squares, but they can also be readily solved as the least square problems, and they are very efficient and reliable solvers for the linear programming problems. But still, the problems which demand real-time computation are challenging. And one of the methods to solve linear programming problem is the interior point methods, and these are very efficient in solving the linear programming problems. So let's discuss the convex programming problem. So as we have discussed, the objective and constraint functions in the convex programming problem are all convex, and mathematically this is just minimize f naught of x subject to constraints that each f of x is less than or equal to bi, where we have m such constraints, and each fi is convex and it should satisfy this condition. Fi of alpha x plus beta y is as equal to alpha times fi of x plus beta times fi of y, where x and y are vector in Rn, alpha and beta are non-negative, and alpha plus beta is equal to 1. So if any of the fi's, where fi includes fi's constraints and f naught of x, is if any of this function violates this constraint, then the problem is a non-convex problem. So linear programming and least square are special cases of the convex programming problems. As we can see, for the linear program, the equality should hold, whereas for a convex programming problem, a weak equality holds. And in general, there are no analytical solution to the convex programming problem. So there are very efficient and reliable solvers for the convex programming problems, and these are interior point methods, subgradient and stochastic subgradient methods for non-differentiable convex optimization problems, cutting plane methods, ellipsoid methods, and if we can exploit any spatial structure or any spatial pattern such as sparsity pattern, then a very large convex program can be solved very efficiently and very reliably. So various forms of convex programming are SOCP, which is second order cone programming, semi-definite programs, geometric programs, which can be solved very efficiently by interior point methods, linear programs, and quadratic programs. So we will discuss all these in the upcoming presentations in convex optimization. And as I mentioned, the SOCPs and geometric programs can be solved reliably with the interior point methods. So the main challenge in the convex programming is to identify that the problem is convex, and once we have identified the problem is convex, or once we have formulated our problem in a convex programming form, then with a bit of exaggeration we can say that we have already solved the optimization problem. So when the problem is neither a linear problem or also not known to be convex, then it is known as a general non-linear programming problem. And in general, there is no available approach to solve such problems like we do for convex programs, linear programs, and least squares. And in general, the solution involves a local optimization, or we can say the solution is a local solution, local optimum solution. So in general, non-linear optimization problem, we seek a local solution because it is very hard to determine the global solution for general non-linear optimization problems, because there can be many local solutions, and we will see that for a non-linear optimization problem, the solution is generally trapped in a local minima. So by local optimization, we mean that the solution is not guaranteed to have the lowest objective value. So if we have the domain of the function, and if we have identified certain value of the variable as a optimal solution, then we cannot guarantee that the solution is the solution will give the least objective value among all the feasible points. So a local optimization problem can be solved very easily, as it requires just the differentiability of the objective and constraint functions, and it also requires the initial guess, that is the initial starting point is crucial in local optimization problem. So consider this problem where we have to minimize, or we have to find the lowest value of this function. And as we can see, if we start from this point and if we use certain descent methods such as gradient descent or conjugate gradient descent, we will see that the gradient will point in this direction, and therefore the solution we obtain will be this solution, which is a local optima. And if we choose a starting point here or here, then we can see that we can identify the global optima of this function. So for local optimization problem, starting point is very crucial and it requires initial guess. So another problem in nonlinear optimization problem is a global optimization, where we seek the global solution. There is a global optimum solution for the optimization problem. So when the number of variables is small, then we can go for the global optimization, and the solution is and the solution takes very long time. It can take hours or even days to find the global optimum solution. So convex optimization also plays a certain role in nonlinear optimization problems, such as the local optimization problem can be initially framed approximately as a convex optimization problem. We can approximate the objective function with the convex functions, and then we can identify the initial starting point, which can obtain a better solution. And another class of problem is the relaxation problems or the combinatorial problems, where we relax the non-convex constraints with loose convex constraints such as SDP and Lagrangian relaxations, and continuous relaxations in 0-1 constraint combinatorial optimization problems, where we relax the constraints such as xi square is equals to 1. So in these problems, we generally determine the lower bound on the original optimization problem, which gives us a rough idea of the value of the original optimization problem. So as I mentioned, in relaxation, each non-convex constraint is replaced with a loose convex constraint and a lower bound is computed. So by doing so, we can make a guess about the value of the original optimization problem. So one such example is a Lagrangian dual. In Lagrangian dual, we relax the original optimization problem. We relax the constraints using the Lagrange multiplier. So we will discuss these things in detail later. So that's it. It was just an introduction to mathematical optimization, and the later presentations will involve convex and combinatorial optimization and various solvers to solve such problems. So thank you for watching. I am Sanjeev from searching.com.